It is perhaps the very definition of cool. The mid-infrared instrument MIRI on the James Webb Space Telescope is now at its super low operating temperature. The James Webb Space Telescope will search for the first galaxies in the early universe and peer through dusty clouds to see stars forming planetary systems. To do so, its instrument must first become extremely cold. On April 7th, one of its instruments reached a temperature of minus 267 degrees Celsius, or just 6 degrees above absolute zero. MIRI was initially cooled in the shade of Webb's tennis court-sized sunshield, dropping to around minus 183 Celsius. Because MIRI's detectors are unique, they must be kept at a low temperature to function properly. This temperature cannot be achieved without using a cryo-cooler dedicated to cooling MIRI's detectors. The MIRI cooler team has poured a lot of hard work into developing the procedure for the pinch point, said Annalyn Schneider, project manager for MIRI at NASA's Jet Propulsion Laboratory in Southern California. Going into the critical activity, the team was both excited and nervous. In the end, the procedure was followed exactly, and the cooler performance was even better than expected. The James Webb Space Telescope instruments are housed in the Integrated Science Instrument Module, or ISIM, which is at the heart of the James Webb Space Telescope. It houses four main instruments: the near-infrared camera, the near-infrared spectrograph, the mid-infrared instrument, and the fine-guidance sensor near-infrared imager and slitness spectrograph. Because all instruments detect infrared light, they must be kept at a low temperature. The infrared emissions are suppressed by cooling the four instruments' detectors and the surrounding hardware. MIRI detects long infrared wavelengths than the other three instruments, indicating that it must even be colder. When MIRI reached minus 267 degrees Celsius, scientists began a series of tests to ensure the detectors were working properly. We spent years practicing for that moment, running through the commands and checks we did on MIRI, said Mike Ressler, project scientist for MIRI at JPL. Everything we were supposed to do was written down and rehearsed, just like a movie script. MIRI is one of four instruments on Webb, the successor to the venerable Hubble Space Telescope that is expected to be equally revolutionary. Webb will be tuned to see the universe at longer wavelengths in the infrared. This means that it must be shielded from all heat sources, including its own hardware, which would otherwise glow in the same portion of the light spectrum that it is trying to detect. To that end, shortly after its launch on December 25, 2021, Webb deployed a massive sunshield. This tennis court-sized membrane provided shade for all of the telescope's critical components. This was enough in the space environment to passively cool 3 of Webb's instruments to their target temperatures under 233 degrees Celsius. However, this isn't cold enough for MIRI, which will only work with the longest infrared wavelengths in Webb's sensitivity range. Our detectors must be less than 267 degrees Celsius, or they will swamp themselves with what we call dark current, Professor Wright explained. If we go above this temperature, the inherent motions of the atoms inside the detectors generate a charge, which is what they'd be measuring above 267 degrees Celsius. MIRI's optics, or mirrors, must be less than 261 degrees Celsius, the UK Astronomy Technology Centre's director in Edinburgh explained. To achieve an even colder regime, engineers at Northrop Grumman in the US developed and built an active cooling unit, or cryo-cooler. The unit is a network of pumps, valves, and piping that drives helium gas at different pressures across the telescope to absorb excess heat inside MIRI and dump it far away from the instrument. The MIRI team can begin preparing for observations now that the operating temperature has been reached. This entails first ensuring that the focusing of Webb's massive 6.5-meter-wide mirror works as well for MIRI as it does for the telescope's other instruments. Then there's the calibration work, which involves ensuring MIRI is delivering data from its camera and spectrographs in the expected and understood manner. All of this will most likely take a few months. MIRI's internal mechanisms will need to function for at least 20 years. MIRI's camera will eventually provide us with panoramic views of the universe, similar to what Hubble has done. Spectrographs will reveal the chemistry, temperature, density, and velocity of many of the objects in view. James Webb has a number of objectives, including searching for the very first stars to shine in the universe and studying the formation and evolution of galaxies in great detail. MIRI will be a part of it all. 4 coronagraphs are among its smart technologies. These are small discs that are positioned across the field of view to aid in high-contrast imaging. In addition, they will allow Webb to block out a star's glare in order to study only its orbiting planets. The coronagraphs are mounted on a wheel of various imaging filters created by the Max Planck Institute for Astronomy in Heidelberg, Germany. Well, that's all for this video. Thanks for watching. We hope you learned something new. If you did, please like this video and subscribe to Curiosity Lounge for more videos like this.